Swayam Prabha. Digital India. Educated India.
Hello and welcome to another lecture on control systems. So in the previous lecture we have seen how to design PD compensation, and then followed by it we saw that if we design a PI compensator we end up with a PID controller which is capable of meeting the requirements insofar as the steady state behavior, the steady state error is concerned, as well as the transient behavior, for instance percentage overshoot and things like settling time or maybe even rise time, peak time, etc., etc., right. We have seen how to design that, but we have seen, we ended with a caveat. We saw that at the end of the day you must always invariably try out using a simulation to see if indeed the system behaves as you want it to, right. Now this is something that cannot be bypassed using any of those classical compensator design techniques that we might employ, okay, until we go into modern control methods like state space based controller design methods. This is something that we'll have to carry on with, right, this dependence on simulation, right. There's no nice clean analytical results which will tell you exactly that these are where your poles are, where your closed loop poles are, right. So anyway, that will be actually serving as one of the motivations behind state space methods. Nonetheless, we still told you in the previous lecture that, well, it might seem like this PID controller or this PD controller are the panacea, right. They behave like panacea, they like the cure to all of our problems insofar as meeting the performance criteria and the steady state error behavior are concerned. But that is not quite true. So we've already seen earlier in quite a few lectures back that there are these circuit elements called operational amplifiers which are active elements. It turns out that in order to implement these PD, PID controllers, you will actually need such op amps. Yeah. So if you want to actually implement a controller using passive elements which are less costly, yeah, then because they just involve resistors and capacitors, right. So if you want to implement your controllers using such elements, then you cannot actually make do with these PD, PID controllers. So that is why we have to go for an approximation of these PD, PID controllers, and once again the same things carry forward, that is you still have to perform simulations, more so in case of a approximation of a PD controller by a lead compensator or a PID controller by a lag lead compensator, okay. So that is one of the must. The steps will be very similar. The only things that will change are at some subtle junctures, and you will see why those changes come in. You see, the moment you introduce this PD block, it has a transfer function like S plus Z. It's an improper transfer function to start with. Also, apart from the fact that it requires active elements to implement this, there's also this factor that PD controllers can be noisy. Why do I say that? So suppose you have A sine omega t, right, and if you pass it through a differentiator, then what you get is A omega sine omega t. Now suppose omega is high, if omega is high, then this signal gets amplified. So suppose your noise has high frequency, then A omega increases, right. So if noise has high frequency, then this derivative action has the effect of amplifying noise, and typically noises are of signals of higher frequency, right. So that's why it's bad. So more than one reason actually to go from this PD block to this lead compensation, right. What does a lead compensation have in addition to a 0? Well, quite simply it has just another pole that is strategically placed. So this we'll call a lead compensator, which is kind of an approximation for a PD controller, where of course P, Z are both greater than 0, and in addition you have this P is greater than Z. Okay, so your pole is more to the left. Okay, your pole is further to the left than your 0 is for a lead compensator. That's what defines a lead compensator. All right. So why do we go for this, and how do we design this? Already we've seen the why question. Sorry about that. We've discussed this. That this, because this is improper, difficult to implement using, in fact impossible to implement using passive elements, and also standalone PD controllers are noisy. In fact, when we do Bode plots, you will see that sometimes this introduction of this pole, sometimes this pole is also called a roll-off pole. Yeah, it's called a roll-off pole because you have to have a pole. You cannot just realize a PD controller as it is. Yeah, maybe this pole is very far to the left compared to the 0. So it's called a roll-off pole. We'll see why this term roll-off comes into being when we study Bode plots. The physical significance of this will be clearer. Why is it called a lead compensator? That can be actually understood even using root locus. Of course, using Bode plots also we will get a picture of why it's called a lead compensator. But using root locus as well, we will see why it's called a lead compensator. So here's the idea behind the lead compensator. Let's go back to the example, the kind of examples that we had considered earlier, like so. So you have these, so I'm not labeling them anymore, you have these 3 poles, right, and we had sort of seen that if you place a 0, let's say somewhere over here, the compensator 0, that is the PD controller 0, then it had the effect of modifying the behavior of the root locus like so, and eventually you had some root locus emerging like so, in all likelihood. Right? Yeah. So this is it. So what, you might ask, did this 0 do? This 0 actually allowed us to place our closed loop pole in such a way to meet this defines settling time, this defines a percentage overshoot. So meet both these goals together simultaneously. Yeah. How did it do that? You see, the 0 added some positive angles in the angle criteria, right? So this theta z. Yeah, that was the only role of this 0, no? We saw that we had to meet this condition that theta z minus theta p1 plus theta p2 plus theta p3 must be some odd multiple of pi. Yeah. So this theta z served to shift this root locus to the left. Yeah, it allowed us to, because the uncompensated system was going out in somewhere in this fashion, remember? So the moment we introduce this this PD block here, this proportional derivative block here, it allowed us to place the closed loop pole at a point such as this. Yeah. Now the question is, can we not do this using a pole 0 paired instead? Of course we can. How so? Now consider this S plus Z upon S plus P. What effect does this have on a point on the complex plane? Suppose this is our PC1, like the desired closed loop pole minus PC1 and minus PC2. So after all, notice that this green fellow, let's mark the green fellow as the, so green is the PD, and let's use this, what else, what other color should I use? Let's use the purple color for the pole and 0 of the lead compensator, which approximates this PD. So what it's going to do is this pair of pole 0 is going to do exactly what this 0 was doing. In what way? So what was this 0 doing here? This 0 was adding this angle theta z here. Now what if I tell you that this this net angle contributed by this is given by theta z minus theta p. right. So let's call this theta z1 and p1. So let's call this theta z1 minus theta p1. So in other words, what I am saying is, suppose I design a lead compensator of the form s plus z1 upon s plus p1 such that theta z1 minus theta p1 is equal to essentially theta z, which was basically the lead provided by the PD controller. Yeah, then I should be able to manage this. Now clearly what is holding me back is this theta p1. This theta p1 is going to reduce this. So clearly this theta z1, needs to be larger than theta z alone, no? Because remember, theta z1 has to compensate for this negative contribution of theta p1 and yet equal theta z, right? So these are all positive angles. So therefore theta z1 has to be positive. If theta, it has to be greater than theta z. So if theta z1 has to be greater than theta z, then the geometry tells me that I better place my theta z, z1 somewhere here. So let me call this as my, so this is minus z, this is minus z1, yeah, so that this is now my theta z1, and let me place the pole here so that this is my theta p1, and now I have this theta z1 minus theta p1 is equal to theta z, and I am done. This is the approximation of the PD controller by a lead compensator. So that is why I told you a PD compensator is the extreme case of a lead compensator where there is no lag because of no pole, right. So that is why it gets its name lead, because it is taking over the job of providing some phase lead, some lead of an angle at the desired closed loop pole location, which was originally being served by this PD block. So now this lead compensator is doing exactly the same job. So if I view it geometrically, this has a nice interpretation. Now you see there is a lot of flexibility I have to play around with. As long as my theta z1 is to the right of theta z, I can place it anywhere. Yeah, I can play around with this theta z, this z1 location. Of course, once I put it to the left of theta z, left of z, minus z that is, then I cannot meet this, because then theta z1 will be less than theta z. So that this will be violated. Yeah, so therefore this theta, this minus z1 must be to the right of minus z, right, and of course this minus p1 should be to the left of minus z1. So that is exactly what this condition is saying here, right, that is exactly what I said. So this pole must be greater in magnitude than the 0, in other words the pole must be to the left of the 0, okay. So let us look at this geometrically. A beautiful geometric interpretation is, so suppose this is your desired closed loop location, and suppose this is the angle that was provided by the original PD controller. So now you measure of this angle, and using a sort of a divider, what are your valid locations? So you now take this in the next figure, fix up this point and take an angle such as theta z here, yeah. So this is one possible place where you can place your pole 0 for your lead compensator. Additionally, this is another place, provided this interior angle is theta z. Remember, why is this interior angle theta z? Because this is theta z1, this is theta p1. So obviously this angle is equal to this plus this. Exterior angle is equal to sum of interior opposite angles, right. So this theta z1 is equal to theta z plus theta p1. So provided you, for example, take this as your center and draw these sectors of angle theta z, yeah, you will see that as long as you do not cross this green line, the moment you cross this green line and if you draw this theta z, then it will become a parallel line, yeah, because this theta z alternate angles, then this is theta z and this is theta z, so alternate angles, they form parallel lines. Yeah. Until you cross this theta z, any point to the right of minus z is a potential point to place your lead compensators 0. Okay, so everything else remains the same. The only principle here is we'll follow exactly the same sequence of steps for designing a lead compensator, except for the fact that we now have an additional pole to account for, and that's what's imposing this restriction, that now we must place our 0 to the right of this extreme 0 that was placed by the PD block. So wherever that minus z was sitting, any point to the right of this is a potential point. Of course, we don't want to go to the right half plane because that will make it unstable. We don't want to place a compensator's pole in the unstable region, right? So this is R, this is JR, right? So any point within this zone is a potential point, and I can meet safely the angle criteria by satisfying this condition. Okay, so this is how the lead compensator approximates the PD controller. Now, in addition, remember in the last step of the PID controller design, what we did was we placed these pole 0 paired, yeah, and we call it like some let's say some S plus Z upon S, where Z is very, very small. Yeah, Z is much, much smaller. Z is almost close to 0. Yeah. So this led to this nullification of this error. Now the question is, can we do something similar to a lead compensator approximation for this PI block? So this is a PI controller. Yeah. The question is, can we do something similar to this lead compensator like approximation for a PI block using something called a lag compensator to approx a PI controller? Because if we can, then it's good. Why is it good? Because remember, again, a PI controller also necessitates the use of active elements like op amps, but a lag compensator, if it's just a pole 0 pair, the only difference in this case being that this is S plus Z2 upon S plus P2, where of course P2, Z2 are both greater than 0, the only difference being now that Z2 is greater than P2, yeah, unlike the lead compensator where the pole was greater in magnitude than the 0, here the 0 is greater. So in other words, the 0 is to the left of the pole. Yeah. So at any point on the root locus, you see, or any point on the complex plane here, you see that the net phase contribution is obviously the phase contributed by this pole is greater than the phase contributed by this 0. So because this angle is equal to this angle plus this small angle here, right? It appears like a small angle. So therefore, the net contribution of this is theta Z2 minus theta P2, and since Z2 is greater than P2, theta Z2 is less than theta P2. So therefore, this is negative. So it contributes a negative angle. So therefore, it's called a lag compensator. That's why it got its name lag. Yeah. But the question is, you might ask, well, we have seen why a PI compensator works. Yeah, because a PI compensator, we know from our analysis of steady state error that when you have a PI compensator, you have a pole placed at the origin which increases the type of the system. So it makes it a type 1 system. Yeah, and the moment it becomes a type 1 system, we have seen that it nullifies the steady state error. But how does the intuition behind this PI compensator, approximated by a lag compensator work? Because remember, the job of the PI compensator was just to tackle the steady state error. We didn't want to disturb the closed loop pole locations, right? So the lag compensator must also do the same. It should not disrupt the closed loop pole locations. So what we are essentially looking for is, instead of placing this pole at the origin, which would necessitate use of active elements like op amps, can we just place the pole a little off the origin to the left half plane and a 0 close by? So it's like we are shifting this pole 0 pair for the PI controller a little to the left. Yeah, but how does the intuition behind this work, in the sense that how does this lag, I mean I can understand that the pole location is somewhat an approximation of a PI controller, but we must also be sure, at least analytically, or get some intuition behind why this lag compensator also helps us in reducing, maybe not getting a zero steady state error, but at least we should be sure that it helps us in reducing this steady state error at least, right. So here's how. So here's the reason why this works. Notice that again we have this as G0 increases, ESS decreases, because we have this formula that ESS, of course we are considering a step input, it could be applied to others as well, G0, right. Now notice the moment you're introducing this additional pole, I mean let's take the other example, we've already solved for this earlier, the other day, yeah. So here we have this, right. So now suppose this was the actual PI controller, right. So suppose this PI controller's pole 0 pair, we just shifted this entire ensemble a little to the left, just these two, yeah, just these two we shift a little to the left. What happens? Of course it is clearly evident because of the continuity of the root locus that this closed loop pole PC1 is not hampered by much, yeah, maybe the K will change slightly and it will still accommodate for this. But what about the steady state error? Now notice that the steady state error will be given by 1 over, okay, let me go back to the original slide. So it is 1 over 1 plus G0. So what is G0 now? Remember you had this S plus Z. So let's take the case of the PD controller only. So on one hand we have PD and on the other hand we are now introducing the lag compensator approximation of a PID. So this is that, this is K, this is S plus P1, S plus P2 times S plus P3, alright. And now instead of having that S plus epsilon, let's say, yeah, and let's say this is S plus 10 epsilon. Now remember, if epsilon is very small, if epsilon is very small, then in so far as the value of 10 epsilon is concerned, looked at from the vantage point of a closed loop pole, it will hardly make any difference between epsilon and 10 epsilon, right. In other words, what I am saying is that if you are trying to evaluate this gain K and all of these other factors, whether this if you are concerned about whether the closed loop poles that were so carefully placed by designing this PD controller are now going to be trifled with, you need not worry because of the same argument as before. The argument was that after all this pole 0 pair looked at from the vantage point of this vicinity of this closed loop pole, this desired closed loop pole, this pole 0 pair for the PI controller were almost co-located. So similarly, if you now shift this is epsilon, this is 10 epsilon. So this epsilon 10 epsilon might look like a large scaling factor when viewed from the origin. Note, so it's about where you are viewing it from. If you are viewing this epsilon and 10 epsilon from the origin, it's a 10-fold increase. But if you are viewing it from this point, which is much further than the origin, yeah, then this epsilon and 10 epsilon are hardly distinguishable. So therefore, nothing else changes. The only thing that changes is now when you let S tend to 0, essentially what you are doing is you are viewing this from the origin. That is why I was trying to focus your attention back to viewing from the closed loop pole and viewing from the origin. See, when you are saying it's G0, what you are saying is you are basically looking at all these phasors when they are joining these poles and zeros to the origin. After all, what is this? See, when you are putting this S is equal to 0, you are basically drawing all these phasors. So you are starting it at minus Z, ending it at the origin. You are starting this phasor at minus P1, ending it at origin. This at minus P2, ending it at origin. This at minus P3, ending it at origin. This you are starting at minus 10 epsilon, ending at origin. This you are starting at minus epsilon, ending at the origin, and you are measuring the lengths. Now compared to viewing from the origin, when compared while viewing from the origin, the distance of this and this is 10-fold times. So therefore, you see, if this was your PD compensated block and then you add this sort of a lag compensator to it, what you then have is basically 10 times increase. So if you call this, so let us say G bar 0 is the value of let us say Kp for, that is the position error for the PD compensated system, right, and G0 is the same value, or rather the value of Kp, let me be very explicit here, is the value of Kp for PD plus lag compensated system. Yeah. Now you see that this is going to be, we can write this as G0 is equal to almost 10 times, at least approximately, maybe there is a slight change in this closed loop pole location due to this placement of this pole 0 pair, but this you can already see that this is almost 10 times improvement. And if you are increasing this, if this G0 is increased from G bar to 10 times G bar, then of course the steady state error will also come down. So although we have analyzed the effect of adding a pole at the origin and seen that it completely eliminates the steady state error, even if you are not placing your pole exactly at the origin, but if you are placing a pole 0 pair very close to the origin, it has almost the same similar effect, that of decreasing the steady state error. So now combining the pieces together, we have seen that a lag compensator approximates a PI compensator in a PI controller insofar as decreasing steady state error is concerned, and a lead compensator does a very good job of approximating a PD controller insofar as meeting those transient performance specifications are concerned. Putting these two together, it stands to reason then that a lag lead compensator should be able to approximate the effect of a PID controller, and this is good. Yeah, this is good because if this is possible, yeah, and indeed we have argued, we have shown you, taken piece by piece together, we have shown you that this is possible. So if this is possible, then it is good because now we do not need to resort to use of op amps, and we will also be able to eliminate this noise that is always amplified because of the use of a PD controller or a derivative action. Yeah, so we can replace all of this with simply a lag lead compensation. So instead of like taking an example or figures like this, let me just take a concrete example and I will actually show you with including simulations how this works. Okay, so here is the example. So suppose you have G of S is given by K by S plus 1, S plus 2 into S plus 8. Okay. So suppose it is said that the closed loop system that is uncompensated yeah, has 20% overshoot. So the design requirement is your user is, let us say, specifying that without increasing the percentage overshoot of the uncompensated system, yeah, without increasing, at best you should keep it at least at 20%, not more than 20%. You can reduce it, maybe it's good, it's better, but you should not increase it beyond 20%. But here's what you do: improve the settling time by halving it. So you are basically making your system faster, twice as fast. Halving the settling time means you are basically entering the 2% band in half the time. So you are basically deciding that your system is faster. In addition, also improve steady state error by a factor of 10. Okay. So remember, all of this is now being specified as with respect to the uncompensated system. So no one's actually giving you some numerical values as in saying, I mean that would have been a little easier. Then you would have known that this is what I have to shoot for. I have to actually target a settling time of this and a steady state error of this. Yeah, those numerical values are explicitly not given. So this is suppose some sort of a user who is specifying for you the design requirements in fuzzy terms. So lot is still left for you to figure out. In what sense? In the sense that now you have to actually analyze this uncompensated system and find out what in reality the settling time of the uncompensated system is. Only then you will know what half of that is, and then you will try to meet that. You will have to also figure out what the steady state error for the uncompensated system is, and then you have to reduce it by a factor of 10. Yeah. So then our first job is to draw the root locus for the uncompensated system. Yeah. So of course I have already solved this problem in rough, so that's why I will probably be able to do it a little quicker. But you should verify. Of course I am making some simplifying approximations in numerical values, but yeah, it shouldn't be too much of a problem. But you should still verify. You should do these calculations with me. Maybe if needed, pause the video and try out these computations on your own. Okay. So let's quickly figure out what the uncompensated system's response is like. So we have one at -1, we have one at -2, 2 poles, and we have a pole at -8. Okay. So another point that I might have missed out, recall in an earlier lecture we had said that when you have additional poles and zeros and you want to approximate them as a second order system, then you don't just drop off the poles and zeros in the open loop stage. You just close the loop around it, and then you see if it meets the 5 times criteria. So that is very, very important, because here you see, we know that there are 3 poles here, and if you had dropped this third pole from consideration, then you would have drawn incorrectly that the root locus looks something like this, and you would have been completely off in your analysis. Yeah. So only after in the closed loop pole configuration, when you figured out that your desired closed loop poles are somewhere, then you figured out where this third pole has migrated to. If it meets the 5 times dominant pole criteria or is nullified by some 0, right, then you would be able to rest easy. Okay. Right. So since we haven't been that naive, we haven't cancelled out this third pole, we will be able to draw this uncompensated system's root locus. It will look something like this, because there are 3 branches, and of course this branch goes towards that side, and there is no root locus on this segment, on this particular portion of the segment. Yeah, right. Now you see that based on this, I am now given what information? I am told that there is a 20% overshoot. So if there is a 20% overshoot, let me figure out what the value of zeta is. So basically what I am then going to compute is e to the minus pi zeta 1 root 1 minus zeta squared is equal to 0.2, which will then tell me that zeta is equal to 0.456. Of course I am cheating because I am not using a calculator here in real time. I have already computed these a priori, so I know what these values are. So with this zeta, right, I can draw this constant zeta line here, having evaluated this zeta for this 20% overshoot, and then I am going to draw this line, and then I know that this is where the pole of my uncompensated system is. In other words, if I had this k by s plus 1 into s plus 2 into s plus 3, yeah, in closed loop like this, sorry, this is minus, yeah. So if I had this in closed loop like this, then this would allow me to determine k. Why? Because now I know that this is my uncompensated system's closed loop pole. Alright. So I have found out this intersection, and I figured that, so this angle has to be then 62 degrees is what I figured for this zeta is equal to 0.456, this has to be 62 degrees, this has to be 28 degrees, I think, yeah, this has to be 28 degrees. So accordingly, I have now figured that this particular pole for the uncompensated closed loop system, this pole is at minus 1.135 plus minus, so of course this is a pole means this is also a pole here, it is conjugate. So of course the top one is just the positive imaginary part, so this is plus j 2.313 approximately, okay. So I figured that this is the closed loop pole which actually gives this uncompensated system a 20% overshoot. So once I figured this out, from this point then I draw these line segments, and I take their product. So this, call this L3, call this L2, call this L1, and I figured that K is equal to L1, L2, L3. Of course I can also compute, again I can cheat, but you know, if you do this then you will get that K is almost equal to 38, yeah, K is almost equal to 38, that is what I computed, okay. Now I have figured out what the uncompensated system is like. Now look at what I have been asked to do. I have been told that I have to improve the settling time by halving it. So what is the settling time here? The settling time is given by this real part. So this is responsible for settling time, right. So what is the settling time? The settling time Ts is equal to 4 over 1.135. So if I have to halve this, I have to basically double this, yeah. So that will tell me my desired closed loop pole. So desired closed loop pole needs to have a real part equal to 1.135 into 2, which is 2.27, minus sign of course, yeah, with a minus sign, because it is got to be on the negative side, yeah. So this is at minus 2.27. So then let me place that desired, let me locate that over here, yeah. So this is basically, okay, it should be a little to the left of 2. So let me erase this, yeah. So let me place this here, a little to the left of 2. So this is crossing at minus 2.27, yeah, minus 2.27. All right. So now that I have figured this out, and I know why is it here, because I know that it must meet the percentage overshoot condition. So if it has to meet the percentage overshoot condition, it must be at least on this line, if not below. So let me at least place for now at least on this point. I can of course place it below here. In that case the percentage overshoot would be less than 20%. Yeah, so that is some flexibility I have. At most it should be 20%, not more than 20%. So for now let me just restrict it at 20%, and the moment I figure this out, because the ratio, so notice the ratio of this and this must be the same as the ratio of the, because this constant zeta line is telling me the ratio of the real part and the imaginary part. So I have found the ratio of the imaginary and the real part for the uncompensated systems closed loop pole. Now that same ratio will be there for the compensated systems closed loop pole as well, because we are still settling for the same, we are still agreeing to have the same percentage overshoot and hence the same zeta. So therefore the imaginary part I can, part of desired closed loop pole I can have at, let me figure that out, yeah, so I figured this out, this is 4.425, yeah, 4.425 plus minus, yeah, plus minus j 4.425, yeah, you can omit the j because we have already said it is an imaginary part, does not matter. So it's, so basically then we know that we are required to place, so now look at this another diagram, we have this minus 1, minus 2, minus 8, and we have been given that this is where we desire our pole to be minus 2.27 plus j 4.425. 4.425. This is the desired location. So at this point we must meet the angle criteria. In other words, we must place our lead compensators pole 0 pair in such a way that it meets this angle criteria. So what's the first thing I do? I draw these lines and I find out the sum total of these angles. Yeah. So I figured that the sum total of these angles, yeah. So I figured that the sum total of these angles I have computed. So this is theta 1, theta 2, theta 3. So I figured that sum total of theta I from 1 to 3 is equal to 237.18 degrees. So now if I want to place a extreme case, let's say I want to place this PD. If I wanted PD compensation, then the 0 of PD controller needed to be such that theta z minus 237 degrees, 0 of the PD controller, say z, needed to be such that theta z minus 237. So theta z is basically, you place that z here somewhere and you look at this. So 237 degrees is equal to let's say minus 180 degrees. Yeah, because this is the closest I could get. If you push this 237 to the other side, so therefore theta z is equal to 57.183 degrees. 18 degrees, let's drop the 3, yeah, 57.18 degrees, yeah. So basically then I have to find the point from here that subtends 57.18 degrees, and that would be my PD controller. But remember, I am not trying to design a PD controller, I am trying to design a lead compensation. So I have this flexibility of placing this 0 because I know that there is a pole. So if I now compute this, yeah, then I reckon that this, yeah. So basically then this tells me PD controllers 0 would be at minus 5.123, okay. So that tells me that if I wanted to place a PD controller, I would have placed it at somewhere over here minus 5.123, yeah. But now I have more flexibility to play around with because I can place the 0 anywhere to the right of minus 5.123 and then compensate the remainder with a additional pole for the lead compensator, right. Remember this picture, remember this, where was it, yeah, so here I guess, or maybe, yeah, where was I approximating it, yeah. So here remember this picture here, the same angle has to be subtended, right. So long as my lead compensator 0 is to the right of the the PD controller's 0, I can always place a pole and 0 pair to meet this angle criteria, right. So that is exactly what we are now going to do. The only difference being that now it might be tempting. So notice, you might often feel, okay, so since I have this entire flexibility, let me try to cancel out this pole. That way, in the open loop at least, it will be a pure second order system, yeah. Wouldn't that be nice? So what if I sort of place this 0 over here, so that when I add this pole, I will have at least one less pole to deal with, because remember, if I am adding a pole 0 pair, it will now have 4 poles and 1 0. So now if I cancel out this one pole here with this 0, then I will still have, after this cancelling out, just 3 poles and no 0 to deal with. That simplifies matters a lot, no? Because now I have only 3 parameters, but if I don't cancel it out, then I will have 5 parameters, 4 poles and 1 0. right? It might be very tempting to do that, but remember, tempting as it might sound, it might not always lead to the best compensator design. It might work in some cases, I agree. It might simply, in cases where it will work, it will actually, and that's why this controller design is a bit of an art. Until you go to this last step of verifying using simulations, you'll never really figure out what was best. Okay, so do not always fall for this trap of trying to cancel out a pole and zero. In textbooks you might see some examples where they cancel out this pole and zero, this pole of the plant using a compensator 0, but it may not always work like a charm like they show you in a textbook example. Okay, be very careful about that. So in this case I am not going to do that because I actually tried that and it didn't work here. Okay, right. So what I decided to do was, after giving it some thought, okay, where did I place the, so of course you are free to try this out. There is a lot of subjectivity, as I said, it is like an art. So there is a lot of subjectivity as to where you put this this 0. Yeah. So here's what I did. I think yeah. Okay. So I chose the ZC is equal to minus 4.5. So I didn't cancel out this pole 0, I didn't go for this cancelling out business. So I chose it at somewhere over here, and I figured how much angle it contributes, and then this remaining angle, yeah, this 57.18 degree I drew from here and then extended it here. So this angle was 57.18 degrees. So this was, remember, this was arbitrary. This minus 4.5 was my arbitrary choice. This is where you have freedom to play around with. This is not hard and fast. So once I drew this minus 4 this pole at minus 4 this 0 at minus 4.5, I joined this line, and from this line I drew this 57.18 degrees and extend this here, and wherever it cuts this real axis is where I place the pole. So this then turned out to be, by my computation, as minus 43.87. Okay. So basically, in summary, what I chose was PC is equal to minus 43.87. Okay. So here's what it turned out for me, S plus 4.5 upon S plus 43.87. Okay. And what else did I do here? What I also did was, I have to compute now the K. Yeah. Remember, we have to compute the K, otherwise the design is not complete, no. So I computed this K, and this K came out to be 1247.5. How did I compute the K? I placed this, I measured off all these lengths, this length. So I measured off the lengths of all the poles, multiplied them together and divided by the length of the line joining this desired location to the 0. Yeah, it came out to be 1247.5. So basically then, after this compensation, I have 1247.5 times S plus 4.5 times, okay, no other 0 was there, divided by S plus 43.87 into S plus 1 into S plus 2 into S plus 8. So this is my lead compensated system. Yeah, this is my lead compensated system. But remember, there's one thing I haven't addressed yet in this problem statement. It has also asked me to improve the steady state error significantly, right, by 10 times. So I had to evaluate what the steady state error for the uncompensated system was. I actually did it, but I forgot to mention it in the design process. I got a little carried away. So let me tell you what the steady state error, what I figured was. Yeah, so the steady state error, if I computed here for the uncompensated system, let's see. Yeah, so this was the plant. So let me make an aside here. So once I have evaluated this K as 38, then of course this is nothing but 1 by 1 plus 38 upon 6, I suppose. No, is 8, no? This was what? S plus 8, S plus 1, S plus 2, S plus 8, yeah. Yeah, so this was going to be 8 to the 16, yeah. So this is a little more than 2, so this was almost coming out to be 29.6%, yeah. So this was 0.296 was the steady state error to a unit step, yeah. So if I have to improve that, then I have to get a 2.96% error. So that's got to be my goal, alright. So this I hadn't mentioned earlier, so now note. But now after doing this lead compensation, if you notice, there has been a significant improvement in the steady state error already, okay. So what I do notice now is, if this is my G lead compensated S, then you see that this, I put this G lead compensated S at S is equal to 0 and 1 plus this and 1, this I evaluated and I found that already this is 0.111, which tells me that from a 30% error, close to a 30% steady state error earlier for the uncompensated system, even without using a PI compensation or a lag compensation, right, just by using this lead compensation, even though it was not its original purpose, mind you, the lead compensation's original purpose is to tackle the specifications in terms of transient response, but still it does a very good job of reducing the steady state error. From 30% it has brought it down to 11%, but I have to bring it down to 3%, so I have to reduce it even further, right. So then what I do is, so I'll show you the simulations right at the end. So, but be sure that when I was designing this, at every step I was simulating this, okay. So I will show you the simulations right at the end. So then I need a further compensation by a lag compensator, which would serve like a PI controller. So what I then need is, let me design my specification. So what I need is 1 by 1 plus G lead lag compensation 0 is equal to 0.0296, yeah. And this, what is this? So the lag compensator, of course we don't want the K to change by much, so the lag compensator is going to be just basically, so let me just write that down. So this, we'll approximate this by JLLC 0, that is the value of this lag lead compensated system at S is equal to 0 is almost equal to the 0 of the lag compensator by the pole of the lag compensator times G0 for the lead compensated part only. Let me explain that a bit. So here is what we have already obtained. We have already seen that based on this value that we obtained, the steady state error is 0.111, that is an 11% steady state error. Now we want to place the 0 and the pole pair of our lag compensator in such a way that by scaling it by this lag compensator 0 by the lag compensator pole, when we plug this value in here, yeah, it gives us this. So this we already know. We already know, you can reverse compute this. No, actually not reverse compute, you can just plug in 0 here and you can compute this. Actually based on this computation, when I plug it in here, I got this 0.111. So now you can just plug it in here. So now we can determine this ratio. So this is the only unknown, but from this equation, putting together these, we can determine this. So I determine that ZLC upon PLC is almost equal to 4.1 times, and that makes sense in some way, because of course this 1 is there, but you can see that, you know, if you have to bring it down to 3% from 11%, it's almost a reduction of 4 times, yeah. So you have to increase this by 4 times, this denominator by 4 times. So after a certain point, this 1 doesn't make any difference because this is a very large value, yeah. So you increase this by 4 times and this will reduce by 4 times. So in order to increase this by 4 times, you better multiply it by a factor which is 4. So therefore the ratio of the 0 to the pole is 4. So again here, because nothing much is at stake and I am sure that this at this desired, looked at from the vantage point of this, when I place my, okay, let me use the red color, when I place my pole 0 pair for the lag compensator here, very close by, these will hardly make a difference either to the k or to the total phase angle. Maybe I will have a small shift around this, but that is acceptable to me, because after all this is an art, as I told you, not exact computation. This is meant to be serving as a graphical technique after all, right. So then we have this z is equal to 4.1, yeah, and once we have this, I just arbitrarily chose, this is again my choice, so I just chose this PLC to be 0.1 and ZLC, that is the 0 of the lag compensator, to be 0.41, yeah. So my overall controller then I chose as 1247.5 times S plus 0.41 upon S plus 0.1, that was the lag part which I designed last, then the lead part which was S plus, let me go back, 4.5 and 43.87, 4.5 divided by S plus 43.87 times now the original plant, which was 1 over S plus 2 into S plus 1 into S plus 8. So now I am claiming that if I put together this block in closed loop configuration, unity feedback, yeah, this block when put together in a closed loop unity feedback configuration should have no more than 20% overshoot, should have no more than 3% percentage error, should have a settling time that's about half of the uncompensated system's settling time, right, and it should meet all of these criteria by virtue of me designing this lag lead compensation. So let's test it out against MATLAB Simulink model here. So what I have here is, you look at this, this is the uncompensated system, so you have a 0 at minus 4.5, oh this is lead compensated, I am sorry, let me go for the uncompensated, yeah, so this is the lead uncompensated, so you have a gain of 37, yeah, 38, almost close to 38, and these are the poles, right. So let's take a look and verify for ourselves. Okay, okay, so it has run its time. So let's look at this plot. This is going to be, so I applied a step input. So you already see that there's almost a 30% error, no? It's settling at a value of 0.7, and you see there's almost 20% overshoot, because this is at 0.7 and this is at 0.84 or thereabout. So 0.14 by 0.7 is about 20% overshoot. That is also there, right? So that was the uncompensated system, no mistake about that. Now once I have done the lead compensation, you see immediately it has come down, the peak time has moved to the left, the settling time has also moved to the left, and you see that earlier it was at 0.7, now it's already come up to at around 0.85 or maybe around close to 0.9, I don't know, right. So now, yeah, it's almost close to 0.9, because if it's 11% error, it's almost 0.88, I reckon, yeah. So this is after the lead compensation, and this is reasonably good. So it means that my root locus based design is good, because remember there were so many factors that were there, right. We had to cancel out these poles and 0 pairs, no, otherwise we cannot approximate it like a second order system. But it turns out that for the design that I did, this pole 0 cancellation holds, and that is why this simulation is important. And once this lead compensator worked, then I designed this lag compensator and put it together, and now you see, yeah, so this is almost close to a 3% error. Of course, if I zoom in, you can see this, and it's almost close to a 20% steady state error, I mean 20% overshoot, yeah, and the settling time is almost as good as that provided by the lead compensated system. So I'm happy with this design. So let me show you the design ultimate end. Yeah, this is exactly the poles and zeros that I had claimed I had designed, yeah. So this is the lead compensated systems pole 0, okay. So you see that indeed the design we have carried out has been now verified using a simulation, so you should now feel reasonably confident to go out, but be very careful, you might not get the correct design in the first shot. This is an iterative process, this is kind of like an art, at some level that I use my discretion, 2 junctures particularly. The first such point was when I chose where to place that lead compensator's pole, lead compensator 0, sorry, and the second where to place the lag compensator's pole, Yeah, so those two are subjective choices. So you can try out with the same system for different choices and see the difference for yourself. Okay. Now we will not go into much more detail of this controller design. There can be several other such controller design techniques, such as sometimes people put the controller in the feedback path. Okay, you can find that in several textbooks. There are certain modifications to the root locus based technique, but if you are interested in that, you can read up with the tools that you have now at your disposal. That is, you have understood root locus well enough, you should be able to do that on your own. You should be able to read up and understand that, right. So we have taught you one particular technique of designing this controller, whether it is a PID controller or it is a lag lead compensator, which is an approximate of a PID controller, in the forward path in cascade with the plant. Okay, if you want to put this controller in the feedback path, the design parameters and the design strategy changes slightly, but it is still based on the same basic principles of root locus. So I invite you to go through that as maybe part of a reading exercise. Okay, so in the next lecture we shall focus on seeing how these controllers can actually be now implemented, both using active and passive elements, and then we shall put an end to this root locus based topics and move to something new, such as frequency domain analysis using Bode plots. Till then, take care. Thank you.